Okay, so the next set of exercises on cyclic groups. So this is the first one. We are given, and it has two subdivisions. In the first subdivision, we are given a cyclic group G whose generator is given to be A, and it has order 12. We have to list all the subgroups of G. Now we already know from the text that every subgroup of a cyclic group is itself a cyclic group. So that means we just have to look at the cyclic subgroups of G. That means we should take each element of G and see what the cyclic subgroup it generates. So those subgroups in fact will be all the subgroups of G. So we write the solution like this, and we refer to that theorem also by Theorem 316. Every subgroup of G is cyclic. So it's enough to consider or list, since we are listing them, we are going to list them. All the cyclic subgroups of G. The distinct cyclic subgroups of G are these. One of them is of course G itself, which is generated by the generator of G, that is A. Then we have the cyclic subgroup generated by A square, whose elements are these. Identity of course will be there, and then we will have the higher positive integral powers of A square until things cycle back. So we have A square, then the square of A square, that is A to the power 4, then the cube of A square, that is A to the power 6, then the fourth power of A square, A to the power 8, then the fifth power of A square, that is A to the power 10, and then when we consider the sixth power of A square, it becomes A to the power 12, which is equal to E. That is because G has generator A and the order of G is 12. So A to the power 12 should be equal to E. So that's why these are all the elements in this cyclic subgroup. Then we have the cyclic subgroup generated by A cube, whose elements also can be determined like this, and they are E, A cube, A to the power 6, so this is the square of A cube, then cube of A cube gives us A to the power 9, then the fourth power again becomes A to the power 12, which is E. then we have a to the power 4. So you can see that we are going on considering all the cyclic subgroups generated by these elements that G has, that is A, then A square, A cube. Now we are considering a to the power 4. For a to the power 4, the elements are E, a to the power 4 and a to the power 8, because the next one, a to the power 4 whole cube, again gives us identity because it's a to the power 12. And then if one considers the cyclic subgroup generated by a to the power 5, it turns out that that cyclic subgroup in fact becomes equal to G. So because we are writing the distinct cyclic subgroups, so we are not going to repeat things. So we leave a to the power 5 because that is going to be G. Instead, we look at a to the power 6. So its elements will be E and a to the power 6, because the next power, that is the square of a to the power 6, is again identity because a to the power 12. So this, and of course the cyclic subgroup generated by E, because that's one thing we have not considered in this list yet, which is nothing but the trivial subgroup consisting of only the identity element. And it turns out that the other cyclic subgroups, apparently the other cyclic subgroups which the other powers of A generate, which we have not considered in this list, all of them turn out to be actually one of these that we have written here. So this is a list of all the distinct cyclic subgroups of G. But you cannot of course simply just write like this and claim that these are all the cyclic subgroups. You actually have to look at the other cases also, which we have not written here. So that I leave to you. For example, you have to actually make sure that the cyclic subgroup generated by a to the power 5 in fact is equal to G. Then the cyclic subgroup generated by a to the power 7 also, I think it will turn out to be equal to G. Then you look at the cyclic subgroup generated by a to the power 8, that will turn out to be one of these, like that. The other cases you have to decide. So I leave that to you. Now we turn to the second one. In the second one also we have to list all the cyclic subgroups of this particular group Z12. Now here we know that this is also a cyclic group, since this is a cyclic group of order 12. So it's just like the first case where we considered a general cyclic group of order 12. Here we have a specific one under addition modulo 12, that is the binary operation, order 12 generated by one. Okay, so proceeding like part 1, the distinct cyclic subgroups, because that's what we have to consider. They will give us all the subgroups of Z12. The distinct cyclic subgroups these are. So we just see this list and write this same thing for in this particular case. The first one is Z12 itself, and then the cyclic subgroup generated by A square. In this case, what is A? 1 is playing the role of A because it's a generator. Now, what is 1 squared? Keep in mind that 1 squared actually in this context is not the product of the real number, I mean 2 copies of 1, but rather it is 1 operation 1, where this operation is of course the binary operation we have in this group, which is addition modulo 12. So that's why this is actually equal to 2. So that means this cyclic subgroup in this case is the one generated by 2, and like how we have the elements here you will correspondingly have these elements 0, 2, 4, 6, 8 and 10. So that is this cyclic subgroup in this particular case. So let's write the other ones also. The next one is the one generated by A cube. And A cube for us means 1 plus 1 plus 1. Actually, it's not just simply 1 plus 1 plus 1, but it is rather the remainder when you divide 1 plus 1 plus 1 by 12, and that also turns out to be equal to 1 plus 1 plus 1 or 3. So that is why the next one is 3, and this is 0, 3 and 6. Oh, I think we have one more, 9 is also there. If you try to find the next element in this scheme of things, then you get 9 plus 3. Actually, plus means addition modulo 12. So under that operation, 9 plus 3 is equal to 0. So we cycle back to this, and these are all the elements in this cyclic subgroup. Then the next one is of course this. Then 6, and finally if you want you can list this one along with this, I mean make them adjacent, because they anyway are always there in a group. They are always the subgroups in any group, and then you can determine the non-trivial subgroups. Okay, so in this case these are all the subgroups of Z12 or Z12. So that's the solution. Next, this one also has two parts, two subdivisions. Let G equal to A within angular brackets be a cyclic group of order. This is a little larger than the ones we were considering in the first exercise. That is, it has order 120. 120. List all the elements of order 12. This time we want elements. In G. So that is part 1, and part 2 is this: how many elements of order 12 are there? In a cyclic group of order 1200. I need ink already. Okay, so here in the first subdivision we have to we have to find all the elements in G which have order 12. So we recall one result from a previous section. Let this belong to G. Okay, so we have considered any arbitrary element in G. So it's a cyclic group, so the elements will look like this. And in fact, let us also consider I accordingly. So we mention where because this group has order 120, so we can take I like this. Okay, so now we can say that this is any arbitrary element in G. Then by corollary, this corollary is very useful. 3, 2. The order of a to the power I is 12 means what? If and only if means it's just plus. The meaning of this and the next thing that I'm going to write are the same. This corollary allows us to calculate this order of an integral power of a in terms of the order of a and the exponent I. It is the order of a divided by the GCD of I and the order of a, that is equal to 12. If and only if, because our original group has order 120 and A is one of its generators, so A itself should have order 120. So that means divided by also here also we can write 120 equal to 12. So ultimately now things boil down to this. If and only if the greatest common divisor of I and 120 is equal to 10. Okay. If and only if we go further, so see, the GCD has to be 100, the GCD has to be equal to 10. So the GCD by definition is an integer which divides both I as well as 120. It is already dividing 120, but it should also divide I. So this means, but we cannot just simply write that okay 10 divides I and that's all, because we are not writing a one-way implication, but rather implies and is implied by equivalence. So that's why we write like this: I is equal to 10k, where the GCD of k and 12 is equal to 1. Now let us see whether what we have written here actually is true or not. If GCD of I and 120 is 10, then of course I is a multiple of 10. Okay. Now if this additional condition is not true, say the GCD of k and 12 is not equal to 1, then that means there exists some prime which divides both k as well as 12. Now because that prime divides 12, that prime is either 2 or 3. This is under the supposition that this thing is not equal to 1. So if this prime is 2 or 3, that means 2 divides k or 3 divides k. If 2 divides k, then I actually is a multiple of 20, right? In that case, I will be of this form, 20k prime for some integer k prime. Now in that case, what do we get? Let us see. If this is our thing, then note that 20 divides I as well as 120, because it does. 20 divides I because now I is of this form, and 120 anyway is divisible by 20. So the GCD, being the greatest common divisor, cannot possibly be equal to 10 in this case, because already we have obtained a common divisor 20. So the GCD should be even greater than that or equal to that. So it cannot be 10. So that means 2 cannot divide k and 12 both. If 3 divides both k and 12, then I is of this form. This is the other case, k double prime for some integer k double prime. But then again, like this case, 30 divides I as well as 120, because 30 also, just like 20, it also divides 120. So again the fact that GCD of GCD of this 2 is equal to 10 cannot possibly be true. So that is why 3 also does not divide both k and 12. So this means what? 2 and 3 actually they divide, both of them divide 12. So none of them can divide k, but these are the only possible primes which divide 12. So that means the GCD of k and 12 actually has to be equal to 1. So if this is true, then this implies not only this but this one as well. Conversely, if this condition is true, if I is of this form and GCD of k and 12 is also equal to 1, then you can argue very easily and conclude that this GCD has to be equal to 10. That I leave to you to see that this is actually the case. You start from these things and you show that this is equal to 10. So now we have an idea of what the possible i's should be, and in fact not just possible i's, what the i's should actually be. So we now just simply find the appropriate i's, and that's just it. That will give us the elements whose orders, all of them have order 12. So now okay, but before we write the i's down, let us look at k. Because I satisfies these inequalities, k should satisfy these inequalities. Right? 0, however, no, 0 is actually not a possibility, but still we can write, simply because we are getting these inequalities from these inequalities. 0 is not a possibility, I am saying, because if you take k equal to 0, then I becomes 0, and then the GCD is 120, it is not 10. But we just simply include it. So this end k and 12 is equal to 1, and you in fact don't even have to worry about k being 0, because the condition that this GCD has to be equal to 1 automatically tells you that whatever k is, it is not 0. This is equal to 1, i.e. So what are the possible values of k? So we have to look at those integers k which are, we can say positive, because k equal to 0 does not give you this equal to 1. Those positive integers which are less than 12 and relatively prime to 12. So we carefully write those values down. One of them is of course 1, that is always there, and then 2 is not an option, 3 is not an option, 4 is not an option, 5, 6 is not an option, 7, 8, 9 and 10 are not options, because none of them is relatively prime to 12. So that means 11, and that's just it. So the elements in G of order 12 are, not that we can directly write and write the final conclusion like this. It's because we are not just simply going from here to some condition, but we can go back also. That is why. So when k is 1, you get 10. This is one element whose order is 12. Then when this is 5, k is 5, you get 50, then 70 and 110. So these are precisely the elements in G whose orders all equal 12. Then we come to the second part. How many elements of order 12 are there in a cyclic group of order 1200 or 1200? And for this there is a direct formula, right? And that formula, I have not written the result here. I mean, in the text there is a result which will tell us what that, I mean, how we are going to write the answer. So instead of mentioning that, I mean, instead of referring to that result, you can of course look in the text what we are using here. And it involves that Euler's phi function. So the number of elements of order 12 in a cyclic group of order 1200 is your Euler's phi function value of 12. What does this function calculate? It calculates the number of positive integers less than 12 and relatively prime to 12. And we have already seen above here how many such integers are there. 4. In fact, these are the integers 1, 5, 7 and 11. So the answer is 4. So you look in that section on cyclic groups, which result we have used. This is equal to 4. So there will be exactly 4 elements of order 12 in any cyclic group of order 1200. It does not matter what the group actually is. This one is a purely number theoretic one. Let P be a prime and N be a positive integer. Show that the Euler phi function value, here in this text they are using this variant of phi. If you want, you can write like this also. Of p to the power n equals this. So this is not a very difficult one. So what do we have to show? We have to show that the number of positive integers less than p to the power n and relatively prime to it is equal to this. So we will prove this by looking at how many positive integers there are which are not relatively prime to p to the power n. Since a positive integer that is not relatively prime to p to the power n must be a multiple of p to the power n. So here we are considering those integers which actually are neglected while calculating this value phi of p to the power n. We are considering the exact opposite type of integers, that is those which are not relatively prime to p to the power n. So their number we are going to subtract from the total number of integers starting from 1 through p to the power n, which is equal to p to the power n. Since a positive integer that is not relatively prime to this is a multiple of p, they are these things p. Okay, because we have not mentioned positive integers less than or equal to p to the power n, I think we should mention this. Since a positive integer less than or equal to p to the power n, that is not relatively prime to p to the power n, is a multiple of p. So those are precisely these. There are p to the power n minus 1 of them. And do you see why this is true? It is because if you consider this, say k is a positive integer, forget for a moment this restriction that it has to lie in between 1 and p to the power n, because that's not something we need to understand this thing. This is not equal to 1 means what? That the GCD of k and this is greater than 1. That means that there is something which divides both k and p to the power n, and that something is other than 1. It is a positive integer greater than 1. Now we already know how the positive divisors of p to the power n look like besides 1. They are all powers of p. So that means if such a thing exists, then p should divide k, because there is no other choice. No other prime is involved in this. I mean, if you list the common divisors of k and p to the power n, all the divisors of p to the power n, I mean those among them which divide k will appear, and they are all powers of p. So if something is there which is greater than 1 and it divides both k and p to the power n, then automatically it has to be either p or some higher power of p. So that means in that case, whatever the situation is, p has to divide k. So that's why we have written that those kind of integers which are not relatively prime to p to the power n must be of this form. So these are all these k's. Now their number, which is of course you can see p to the power n 1 times p, 2 times p, up to p to the power n minus 1 times p. Their number is p to the power n minus 1. This we have to subtract from the number of all positive integers lying between 1 and p to the power n, including these two. Hence, the number of those that are relatively prime to p to the power n is naturally just this, and that's what we wanted to show. So this completes the third one, and we will solve the other subsequent ones also, but not in this video. The next one asks us to find those positive integers n for which the order of this group un is 24. Un, recall, is the group of all integers which are less than n and relatively prime to n under multiplication modulo n. So you have to find those n's for which the order of this group is 24. Now we already know what the order of this group is, which is nothing but the Euler phi function value of n. So this should be equal to 24. So you have to solve this equation for n. We will do this in the next video, but let me at least give you an idea of how one should go about finding all those n's which will satisfy this equation. You see, in this section, one of the results is about Euler's phi function itself, and it tells us how to calculate the value of phi of n if we are able to write the prime factorization of n. That is, say the prime factorization of n looks like this: p1 to the power, say, alpha 1, p2 to the power alpha 2, etc., pk to the power alpha k, where the alphas are, the exponents are all positive integers and the pi's are all distinct primes. I am considering positive integers because if 0 appears somewhere, that anyway can be disregarded, that's it. So I am considering all the exponents to be positive. Then first of all, that result says that because phi is a multiplicative function, that calculating phi value at n is the same as calculating these phi values individually and then taking their product. So because of that, we first of all have this. And then in another part of that same result, or in fact we don't have to go there also. Here in this previous one we have calculated this now. So we know what these things are. Minus p1 to the power alpha 1 minus 1, like that. The next one also, you get the idea. Pk to the power alpha k minus pk to the power alpha k minus 1. So this should be equal to 24. Keep in mind, we don't know what these primes are. Also, how many primes should there be, that also we don't know. Further, we also don't know what the exponents are. All those things actually taken together will give us many cases. From those individual cases, different values of n will be found out. So this we will do in the along with other exercise solutions in the next update. So I am ending things here itself. If you want to say something, you can write in the comment section below, or you can mail me at my usual address. The link will be there in the description. So with that, and tomorrow we have again real analysis, where we are going through results on infinite series. I think tomorrow we are supposed to solve. We already, I think we have started solving some of the exercises at the end of the section. So tomorrow we will do more of that. So that's just it. So see you tomorrow with real analysis. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.